Okay, let's continue with this example. Now, let's look at, let's try to find this intersection point. You see that once we find that intersection point, the rest is easy because we have formula for this curve, we have formula for this curve. We'll just do the usual integration business here. Okay, so this is the point where these two curves intersect. Okay, so to find the point of intersection, okay, so I have 2 sine theta must be equal to 1 plus cosine theta at this point. Now cosine theta is square root 1 minus sine square. So let us write it like that. 1 plus square root 1 minus sine square theta. Okay, let us take this one to the other side. We have 2 sine theta minus 1 is equal to 1 minus sine square theta. Now it's begging to be squared. We square both sides. See what happens. 4 sine square theta minus 4 sine theta plus 1 is equal to 1 minus sine square theta. So these ones cancel. I have 5 sine square theta minus 4 sine theta equals 0. From here, I have sine theta times 5 sine theta minus 4 equals 0. Okay, sine theta 0 is one solution, equals 0, one solution, but this is not going to hold when theta is equal to 0 because the circle is here when theta is equal to 0, but the cardioid is not. The circle comes back to this point when when theta is pi, okay, and cardioid is also there when theta is pi. So when theta is pi in our figure, in our setup, let us say. So the second thing is then 5 sine theta minus 4 is 0, or sine theta equals 4 over 5. So theta equals theta 0 as in the triangle. Okay, so this is opposite side divided by hypotenuse. So the other side is 3. So we have our good old. So this, if this is 4, this is 3, it must be shorter. So let me do it this way. So this is theta 0, this is 4, this is 3, this is 5. Okay, so it makes sense. So at this angle, we have this 0. So this is the intersection. So this is theta equals arctangent 4 over 3. Or arc sine 4 over 5, whichever one you find more standard. Okay, so now we can calculate both areas. Let us look at the purple area. Okay, so purple area. So we have two things. So let us again consider typical rays. So one typical ray is like this, the other typical ray is like this. So I have two integrals here. The first one is I integrate r dr d theta. So again, remember that this is dA. Okay. When r is from 0, when r is 0, we are already in the region, and we leave the region here when r is equal to 2 sine theta. And this is true for theta from 0 to theta 0. So this is theta 0. No, this is theta. This one is theta 0. Okay, so this is our parameter is equal to theta 0. So from 0 to theta 0. And then I continue for the purple area from here. So the second one is when theta is from theta 0 to pi. And this time, Again, the ray is in the region when it is 0, and it leaves the region on the cardioid. So this is 1 plus cosine theta, 1 plus cosine theta, r dr d theta. Okay, so you see that now we can integrate it. Which one? Huh? Yeah, I have a plus sign. Okay, thank you. Okay, so this is an easy integral because because of this one, you will get theta 0 someplace, so you get a number there, arctangent 4 over 3. The others will employ trigonometric functions of either theta or 2 theta, and you can again replace it by angles with trigonometric functions of theta, and it will be in this triangle. Okay, the orange area is, I can use this arrow. So orange area is, again, this time theta from 0 to theta 0. And r is from 0 to, no, not from 0. I'm interested in this part. R starts from here to sine theta and leaves the region here, 1 plus cosine theta, r dr d theta. Okay, so you see it's again something doable. So I'll leave it as an easy exercise. Okay, so the other white regions are now easy because here I know the area of this pi. From that I subtract this, I obtain this area. Okay, so there are several variations of this. You put the unit circle somewhere inside or near the cardioid and find the areas, and this is how you do them. Okay, so let's pass to okay, so we have this classical example which we keep doing every time we introduce polar coordinates. Integral of e to the minus x squared from 0 to infinity. This is a function that comes up in probability, so we keep playing with it. Okay, so for evaluate the integral from 0 to infinity e to the minus x squared dx. Okay, so this is something that we cannot do in elementary functions. Most of the time when this is used, it is not from 0 to infinity, but from 0 to some number, in which case you have to use tables. But when it is from 0 to infinity, contrary to common expectation, it is easier and we have an exact value for this. Observe that we can also write this. We can also write I equals from 0 to infinity e to the minus y squared dy. Okay, so now when we multiply them, we get some polar coordinates. We describe the domain of integration of the new integral, double integral in polar coordinates and evaluate it. Okay, so I square, okay, let's say, so I square is 0 to infinity e to the minus x squared dx, 0 to infinity e to the minus y squared dy. And this is an iterated integral, writing Fubini's, if you try to evaluate an iterated integral in which the boundaries do not depend on each other, this is what you do. So this turns out to be from 0 to infinity, 0 to infinity of e to the minus x squared times e to the minus y squared dx dy. Okay? So we are going backwards. If you were to evaluate this, you would notice that the limits of integration with respect to x has nothing to do with y. Besides, this is a constant. You take it out, etc. You come here. Okay, now here we write this now honestly as polar coordinates, e to the minus x squared plus y squared dx dy. Okay, so far it's not integrable, but now the region of integration is this. That's x. Okay, so x goes from 0 to infinity, y goes from 0 to infinity. So this is our region. Okay, we pass to polar coordinates. So let's say pass to polar in short. So the region, the theta goes from 0 to pi over 2. So let me emphasize this, 0 to theta equals pi over 2. And r goes, so a typical ray like this, maybe we should do this systematically. A typical ray enters the region when r is equal to 0 and never leaves the region, so it goes to r infinity. So this is going to be another improper integral. So this is e to the minus r squared, and fortunately I get an r here, dr d theta. Okay, so now we can integrate that. Okay, so let's do that. Okay, so that thing is going to be, you see this part has no theta in it. So we look at this part. It has no theta in it, so I can just put 2 pi over 2. Now let's look at this thing. Well, the integral should be e to the minus r squared. If I take the derivative of this, I'll have minus 2r. Here, I don't have minus 2, so I'll write minus 1 over 2. Okay, so that minus 2 is cancelled with this, and I have r e to the minus r squared. So from 0 to infinity. When we write infinity here, it's always understood that I write some parameter here, say s, and I evaluate this according to s, and I take the limit as s goes to infinity. But we'll do that in our mind. Okay, so this is now pi over 2 times, when r goes to infinity, this is 0. Okay, so 0 minus, when r is 0, this is minus 1 over 2, so plus 1 over 2. So we have pi over 4. Okay, so recall that this is square of the integral that we wanted to calculate in the beginning. Okay, so the integral is square root of pi divided by 2. Okay, plus or minus, but our function is always positive, so we don't even think about negative case. Okay, so this is one nice example which we use every time we work with polar coordinates. Okay, this number is very small. So this is approximately 0.88, not surprisingly, because if you look at the graph of this, you see we are taking the integral from 0 to infinity. So this is x, this is y, and we are trying to find this e to the minus x squared. Okay, so suppose this is 1, this is 1, this is 2. When x is equal to 0, the function is here. Okay, so when you plot it, it is something like this. It goes like this. And from here on, you cannot, the thickness of the ink is larger than the value of e to the minus x squared. So this is the graph. Okay, so this area you see is less than 1. Actually, this also goes very, this part is 1 over e, so it is less than, this part is smaller. So this part is less than 1 over, just 1. Okay, so maybe just to give the idea, I make this a little bit smaller. Okay, so it goes like this. Okay, so it helps to draw such graphs and convince yourself that the number you found algebraically also makes sense. Okay, so any questions so far? Any comments? Okay. Okay, so let's do another example. So this is again a case you don't want to deal with the xy coordinates in finding the antiderivatives. So, okay, I'm erasing this. Okay, so I'll just write the problem. Okay, this is our integral over the region R, which is an annulus region, xy over x squared plus y squared dA, where, so the problem is evaluate this integral where R is, okay, I will just draw the picture. So this is the whole thing. Okay, so it is, no, it is just this part. Okay, so I have this circle of radius 1, this circle of radius 2, y equals x, and apparently we are only interested in this part. So let me make these dotted, x, y. So these are circles of radii 1 and 2. Okay, so you immediately realize that with Cartesian coordinates, this is going to be a little bit hard work. Okay, so you want to integrate this with respect to x. So what do you get? You get ln x squared, and inside it you have y squared, and you'll integrate it with, you have y times ln x squared plus y squared. You have to do some substitution, etc. Okay, so it's going to be complicated. Plus, the limits of integration will involve lots of square roots. Okay, so the first, if you want to integrate with respect to x, okay, up to this point, you'll go from here to here. So x is square root of something here, square root of something here. So if the Cartesian coordinates, this is not impossible, but nobody wants to do it when it is begging to be converted to polar coordinates. Okay, you have x squared plus y squared, so it will be r squared here. Another r will come here. It will cancel one of these. X times y will have another r squared in it. It will cancel. So you don't even have a denominator when you are integrating. Okay, so let's try it that way. Okay. Write the integral in polar. So integral is going to be, so theta goes from 0 to pi over 4, okay, because y equals x is pi over 4 in theta. X, r coordinates is also easy. Okay, so remember, this is always what we have in mind. It enters the region when r is 1, leaves the region when r is 2, and that description is valid on this region. So this is now r cos theta, this is r sine theta, this is r squared, and this is r dr d theta. Okay, so suddenly this looks very easy. So these things cancel. Okay, so you have integral from 0 to pi over 4 sine theta cos theta d theta, because the other part doesn't involve any theta in it. And this is from 1 to 2 r dr. Okay, so this part is easy. Okay, so you do this part, I'll do the easy part. So what is an antiderivative for this? Sine square with a question mark in it. No question mark. Okay, sine square, let's try. Sine squared theta. If I take the derivative of this, I get 2 sine theta cosine theta. I don't have 2 here, so I'll divide by 2. Okay, and this is from 0 to pi over 4. Okay, we'll do that later. And this is the antiderivative of this is r squared, and just like here, I have to divide by 2 from 1 to 2. Okay, let's put the numbers in. Sine pi over 4 is what? 1 over square root 2. I'm taking square, so this is 1 over 2. 1 over 2 times 1 over 2. And this is 4 over 2. Well, okay, 4 over 2 is 2. Minus 1 over 2. maybe it would be better if I did it 4 over 3. So, okay, 3 will come in a minute. Okay, so this is 3 over 2, 1 over 4, 3 over 2, 3 over 8. Okay, so everybody agrees with these numbers? Okay, so in this problem, I didn't pass to Cartesian. Okay, so the next problem, for some reason, I didn't give it a number. Okay, so let's do, any questions so far? You see, these are the types of problems where polar coordinates become useful. Of course, with other types of problems, polar coordinates will have nothing to do. But now we are getting warmed up with problems which are suitable for polar coordinates. Another type is when the integral is given. The region is not described like this as a picture. The region is described by the limits of integration. Okay, so you have a complicated looking double integral in x and y. And there are lots of squares, x squares, y squares, and then the first thing you think is to pass to polar coordinates. Of course, with the integration, let me repeat that they are having more fun than we do here. Okay, with the integration, you always try. Okay, there is no method. You never look at the integral and say, okay, this is the method that's going to work. Okay, with the integration, you look at the method. There are hundreds of problems you solved in your mind. You have some experience there. Depending on your experience, you say, okay, let me try this. This method looks more reasonable for this one. You try it. Sometimes it works, sometimes it doesn't. If it doesn't work, it adds to your experience. Then you come back and you try something more reasonable. Okay, so with the integration, if what you try first fails, you never give up. Okay, it means that you have to make another guess. So now this is an integral where the limits are given. You are just to evaluate that. So let me call this 6. Evaluate the integral which is given. Okay, so let me write this. From 0 to 2, from 0 to square root 2x minus x squared. And the function is dy dx over x squared plus y squared. Okay, so you see nobody wants to attack this problem in this way. It doesn't look impossible at this point, but you see this is probably the antiderivative of square root of x squared plus y squared, but when you do that, you will get an extra y. You don't have y here. Okay, so you are in trouble. Okay, but since you have x squared plus y squared here, polar coordinate comes to mind. You look at this one. This is a circle. Okay, so you have a circle here, x squared, y squared here. So the first thing you try is polar coordinates. Again, the key word is try. If it works, it works. If it doesn't, then we are in trouble. Okay, because by looking at this thing, I can't think of any other approach. So if these things don't work, then you try numerical approximation. Okay, so in order to pass to polar coordinates, remember that was our first strategy, we have to sketch the region so that we can have this red arrow and describe the region. Okay, so this is a circle. You see, I'm integrating respect to y. So the region starts from y equals 0. Y equals 0 here goes to y equals 2x minus x squared. Okay, so everybody understands this. This is the x coordinate, x-axis. This is the x-axis. This is a circle. Okay, so this one is y squared is equal to 2x minus x squared. So you take everything to this side. See that this is x minus 1 squared, x minus 1 squared plus y square. I have an extra one here, so I put that extra one to make it equal. Okay, so this is a circle with center somewhere here, and we are in the upper half plane. So this is, okay, so this is the region. Let us check again. A ray, I'm integrating with respect to y. So a ray parallel to y-axis starts from y equals 0, goes to this circle. And this description is valid between 0 and 2. Okay, so it is all of this shaded region. Okay, so in Cartesian coordinates, we discover what the region was. We read it from this part. Okay, so now in order to pass to polar coordinates, I have to look at this arrow, but I have to write everything in terms of polar coordinates. What is an equation for this circle? Cosine, but if you say r equals cosine, it will start from here. It is here, so 2 cosine. Okay. If you say r equals cosine theta, that's a circle. But when theta is equal to 0, it is here. It goes up. Okay. And then at pi, it is here. So that circle is this one. But I have to go up to here, so I started r equals 2 cosine. Okay, so this is r equals 2 cosine theta. Let's check if we can also get it from here. Okay, so here this is r square sine square theta equals 2r cos theta minus r square cosine square theta. We are going to have trouble here, so maybe I have here r square minus r square cosine theta. Okay, sine square is 1 minus cosine square theta. I have 2r cosine theta minus r square cosine square theta. These ugly things cancel. I have r square equals 2r cosine theta. r's cancel. So r equals 0 will give me only this point, which is already on the circle. So here r equals 0 or r equals 2 cosine theta. Okay. So when you draw this, you see that already on the next solution. Okay. So the next solution is this one. When theta is pi over 2, r equals 0 is obtained. So this doesn't add a new point. You have to check these tiny details because in some complicated problems that obvious solution is not given by the second one. So you have to also plot it. But this is an easy case. So you can either discover this equation algebraically from here, or you memorize a few simple curves. Okay? Everybody memorize that x squared plus y squared equals 1 is the unit circle. So r equals a constant times sine theta or cos theta is a circle. Okay? Depending on that constant, if it is cos theta, it is a circle like this, and that constant tells you where half of that constant is the radius. If it is sine, it is over here. If the constants are negative, then you are on this side or this side. So you just remember a few technical details about these. Okay, so now we killed the analysis of the region to death. Now we can write the integral. Okay, so finally, our integral is equal to, in polar coordinates. So first of all, theta goes from 0 to pi over 2. 0 to pi over 2. And radius starts from 0 and it goes to 2 cos theta. And what am I integrating? 1 over r. Okay, so this is 1 over r is my function. dy dx is replaced by r dr d theta. Okay, so these cancel and this part now doesn't cause a problem. Otherwise, it would make this into an improper integral. We would take limits, but they cancel. Okay, so now we have this. Do you want me to continue? Okay, so integral from 0 to pi over 2. I integrate 2 comes out to cosine theta d theta. What's the antiderivative for this sine theta from 0 to pi over 2? Well, this is 2. Okay, that's what I found. As an exercise, you can check if you can integrate this with respect to theta first. Okay, so we have this integral. How do you now forget about polar coordinates? We have an algebraic expression. We are integrating. Forget that this is r or theta of polar coordinates. Call one of them x, the other one y. Change order of integration. Okay, let's do this as an exercise to stretch our muscles. Okay, so 6 prime. Reverse the order of integration in integral from 0 to pi over 2, from 0 to 2 cosine theta dr d theta. Yes, so first of all, you integrate this. So this is your exercise. I'll just watch d theta dr. Theta starts from where and goes to where? Forget about polar coordinates. Okay, this is just an algebraic problem. The relation between the two parameters are given like this. When it is solvable with respect to one of them, we immediately integrate with respect to that one first. That's the first integral. Now you solve it for the second parameter. So theta goes from 0 up to that value. What's the solution of this? Theta is arc cosine r over 2, right? So theta starts from 0 and it goes to arc cosine arc cos r over 2. And then r goes from where to where? What's the smallest value of r? 0. What's the largest value of r in this region? 2. So the last one is easy. We check that here we don't have any thetas. So at least we are not making a big mistake. So we evaluate this. Okay, the first step is easy. From 0 to 2, d theta, theta from 0 here. Okay, so you have r cos r over 2 dr. What is an antiderivative for this? Well, first of all, we can derive these things. If you have a very bad function here, forget about the definition of bad. Okay, so common sense. If you have a very bad function here, the antiderivative involves x times that very bad function. And then you take the derivative of this, you'll have some extra term. If you are lucky, you can now get rid of that extra term. Okay, so this is one method of finding antiderivatives by hand. So let us look at this thing. Integral arc cos x dx. So we expect that this is going to be x arc cos x plus something here. Okay, what was the derivative? Because in order to find this term here, I have to take the derivative of this. X arc cos x derivative is arc cos x. Okay, so I obtain this one. Plus x times derivative of arc cos x. Does anyone remember what the derivative of this was? It has to be minus. Okay, so this one is minus 1 over square root 1 minus x squared. Because everybody knows the derivative of arc sine, it is obtained like this. Sine and cosine are exactly the same thing algebraically, except when one of them is increasing, the other one is decreasing. So you put a minus sign here. Okay, so this part here is, so this thing becomes minus x over 1 minus x squared. Okay, so I have to put here something whose derivative will be that with the plus sign so that it will be cancelled. Okay, so I put here plus. If I put 1 minus x squared, if I take the derivative, I get minus. So I put minus here. Okay, so now the derivative of this, you see, is plus this, right? Maybe I need 1 over 2 somewhere. No, I have the 2's cancelled. Okay? Do you agree? And of course, you have to put plus c here. Okay, so this is how you find antiderivatives the cheap way. If you have a bad function here, the antiderivative, you bet, you try, okay? It's not a rule. You bet that the antiderivative will start like this, because when you take the derivative, you immediately obtain this guy, this bad guy here, plus you obtain something. So here you must have something whose derivative will cancel this. Okay, so this is sometimes possible, sometimes not possible, but in this case it's possible. So let me check what I have here. Now here, of course, x is r over 2, so now we take all of this and come over here. So this thing is equal to, okay, I have too many arrows here. This is equal to, let me write now what I found here. R times cosine inverse, okay, I'm using arc cosine here, so let me write arc cosine r over 2 minus 2 square root 1 minus r squared over 4 from 0 to 2. Okay, so you see that it's not very bad, because most of these things will be 0 when you put either r equals 0 or r equals 2. So the answer, what is the answer? 2, right? We mentally calculate everything here and we immediately know that it is 2. At least it must be 2, okay? Because in the other way we found 2. Okay, so check that it's really 2. Okay, so okay, let me, since we have 10 minutes, let me find an interesting problem. Okay, they are all interesting. Okay, let me start these volume stuff. We'll do these volumes with polar coordinates again. The region will be nice for polar coordinates. So we'll express the region in polar coordinates, which then will make life easier for the function. But the functions must also involve lots of x squares, y squares in it. So next time we'll look at what happens when it doesn't have x squares, y squares in it. Okay, so this problem 7. Find the volume of the solid that lies under the paraboloid z equals x squared plus y squared. Okay, so this is a paraboloid like this that opens up. Okay, and above the xy plane and inside the cylinder inside the cylinder, x square plus y square is equal to 2x. Okay, so cylinder means that z, in this case, cylinder x square plus y square equals 2x means that z is free. So this is a circle in the xy plane. So you consider all the cylinder that that has its edges on this circle. Okay, cylinder generally means that you give the relation between two coordinates. The third coordinate is free. So you plot this figure on this coordinate, whatever coordinate plane it is, and you just extend it. Okay. So what's happening here is something like this. So now wait a minute. First, let us look at this one. So you see that this is x minus 1 square plus y square equals 1. So this is on the x-axis. So what's happening is I have this circle here. So the circle is here. Again, I'm drawing the picture in the first octant. So let's make the circle center here. So this is our circle here, x, and this is y. And we have this paraboloid going up. Okay. So here, again, it is something like this. Okay. So you intersect it with this. This blue thing is the paraboloid, and you intersect it with this black circle, black cylinder. Okay, so this cylinder goes up like this. Okay, so here again you have something like this. Okay, so try to visualize it. Inside this cylinder, we have this paraboloid. Okay, so we'll just try to find the height. Height is given like this, and x square, y square is restricted to this region. Okay. So this is my region D. From the symmetry, again, if I calculate everything, the volume above this region, then I multiply it by 2, I'll obtain the volume. So volume is equal to 2 times integral over d of height dA. Okay? So height is x squared plus y squared as given here, and d is this region. Okay, so we now write it in polar coordinates because we have lots of x squared, y squares in polar. Okay, x squared, y squared is r squared. dA is r dr d theta. Okay, so I'm reminding myself that this is replaced. Now r, again, let's use this. A typical ray enters the region when r is equal to 0. And when does it leave the region? 2 cosine theta, just the previous problem. 2 cosine theta. Okay. And this is true when theta is between 0 and pi over 2. This is theta is 0. It goes like here when this angle is theta over pi over 2. From 0 to pi over 2. Okay, so you see now it's easier here. Here you are going to integrate x squared plus y squared with respect to dx dy. It looks easy, but this region will involve square roots. Okay, because here, suppose, well, you don't want to integrate with respect to x because you have 2 square roots. So you will integrate with respect to y first. So let us also write this in Cartesian coordinates. This is 2 times integral x squared plus y squared. We prefer to do it with respect to y first, dy. Y starts from 0 and goes to here square root 2x minus x squared, and y is between 0 and 1. Okay, so dx. x is between 0 and 2. Okay, so this is in Cartesian coordinates. The other one is in polar coordinates. So let me see. Okay, let me go over the solution of this, and then we'll stop. So we'll do this one. So that's the last thing we do today. Okay, so we want to calculate this. So here, okay, in my notes, for some reason, I calculated like this, from minus pi over 2. So I didn't multiply by 2. Pi over 2 from 0 to 2 cos theta. I have r cubed now, dr d theta. Okay, so minus pi over 2 to pi over 2. I have r to the 4 over 4 from 0 to 2 cosine theta d theta. So this is equal to 4 times minus pi over 2 to pi over 2 cosine 4 theta d theta. Okay, so at first it looks impossible, but you say this is cosine. If it was cosine square, I would do it. This is the square of that. Okay, I should be able to do that. So this is now. Okay, so I decide at home when I was doing it here, I noticed that I could multiply. I could do it from 0 to pi over 2. So this is now 1 plus cosine 2 theta over 2. This is cosine square. Another square, I have this, d theta. Okay, so here I have 4, 8, so I have 2 here. Integral 0 to pi over 2. I have 1 plus 2 cosine 2 theta plus I have cosine square 2 theta, which becomes 1 over 2, 1 plus cosine 4 theta d theta. Okay, you see now everything is integrable in terms of simple things. So let me simplify this for the last time. 0 to pi over 2. I have 3 over 2 plus 2 cosine 2 theta plus 1 over 2 cosine 4 theta d theta. Okay, so this is going to be 2 times 3 over 2 theta plus sine 2 theta. Okay, so derivative will bring you this 2 plus 1 over 8 sine 4 theta from 0 to pi over 2. Okay, so you see that these will be 0 at 0 and pi over 2 because this is going to be sine pi, this is sine 2 pi, so they are 0 and I get only the answer here. So this is 2 times 3 over 2 pi over 2, and that is 3 pi over 2. Okay, so the only tricky part was not to get discouraged when you see this. Okay, so once you say I'll do it, the rest you see is just easy. Okay, so on Thursday, in addition to our surprise quiz, we'll look at triple integrals in x, y, z. Okay.